Welcome to another one of these videos where I tell you a problem that I have, hoping that somebody helps me solve it. And today we're gonna talk about uncertainty and Hamiltonian mechanics. In particular, I want to understand how the covariance matrix evolve under Hamiltonian evolution. This is something that I understand in the single degree of freedom. And there the constraint is just that the total uncertainty is conserved, and I want to understand this intuition in multiple degrees of freedom. I want to understand how the uncertainty can go from one degree of freedom to the other, and I still don't understand that. In principle, it shouldn't be that hard because it's we're basically just studying how the covariance matrix evolved under the symplectic group, and it's a linear group, and it should be basically just linear algebra, except that there might be some tricks that one has to do that I haven't figured out. I haven't figured out the right trick to understand what's going on. So I'll tell you what I figured out in the single degree of freedom, and then how things sort of generalize, at least mathematically, in multiple degrees of freedom, and the thing that I'd like to get. So maybe somebody that is a better mathematician than me, which is not that hard, can help me understand what I need to do. So let's go to my tablet and I'll start writing things. So first of all, what happens in Hamiltonian mechanics is that you can understand Hamiltonian evolution as essentially preserving the symplectic form, which is in the one degree of freedom. It's a 2 by 2 matrix that looks like this: 0, 1, minus 1, 0, and 1. And so any Hamiltonian evolution preserves this matrix in the sense that if you get the Jacobian and the inverse of the Jacobian times, let's call this omega, times omega, and the Jacobian, this is going to be equal to omega. And we are only going to concentrate on the transformation where this Jacobian is linear, which means the Hamiltonian is going to be quadratic. So it's going to be something like a p square plus b pq plus c, and so on. All the terms that are quadratic or lower. So right, the q squared, the pq, the q squared, the cp, the pq, and the constant. And so these will form, essentially will give a linear matrix to, the Jacobian will be just a constant matrix, and then we can study everything like that. So one of the property of the symplectic group, the symplectic group would be all these Jacobians, all these matrices that can be derived from some Hamiltonian that is quadratic. One of the properties that all these matrices have is that they're going to have the determinant 1, right? So these j's are going to have the properties that all the j's, the determinant of the j is equal to 1. And so if you are transforming any matrix, right? So this j minus 1 aj would be the matrix as is transformed by this symplectic transformation, by this element in the group. Actually, I already had one mistake. These are not inverses, these are transposes. There you go. Sorry about that. Okay, this is how the matrix evolved through the evolution. And what happens is that if you take the determinant of this, of course, by the property of the determinant, you're going to have the following, that the determinant of the product is the product of the determinant, and therefore all of this is going to be just the determinant of A. So the determinant is essentially conserved by a symplectic transformation, which is essentially Liouville's theorem. You're going to have that the volumes are conserved. And so for a single degree of freedom, it turns out that every every matrix that has the Jacobian, every matrix that has a determinant equal to 1 can be a Jacobian of a symplectic transformation, can be a member of this symplectic group. And so essentially any transformation that preserves the determinant of a matrix is something that is symplectic. And so what happens then if we have a covariance matrix, and the covariance matrix is defined as the variance on Q squared times the covariance of Q P, and then the covariance of PQ, and then the variance of P squared. So this is basically the matrix made by all the permutation of the covariance, and then the covariance of a variable with itself is the variance. What happens then during a symplectic transformation is that the determinant of this is going to be preserved, so sigma square Q, sigma square P minus the covariance square is going to be conserved. That part is the same. And so if you imagine what happens, you can write, you can sort of draw a covariance matrix by using an ellipse. And so this ellipse would correspond to a covariance matrix that is diagonal, that is, oops, not this one, that is going to be sigma q square, sigma p square, and 0 and 0, because these lines here are perfectly aligned with the axis, and therefore this here would be your sigma p, and this is going to be your sigma, no, sorry, this is going to be the sigma q, because this is position and this is momentum. And there you go. So if you add a covariance, instead what you're going to be doing, you're adding a correlation between Q and P, and therefore you're essentially slanting the distribution. And so in Hamiltonian mechanics, since you have to preserve this the area of these ellipses, you can essentially change the side. So you can take this and shrink it like that. So you can't change the side, you can change the relative length of the ratio. You can change the ratio, you have to keep the size, and then you can rotate it. So that's basically as much as you can do in this space. So the question is, what's going to happen if we have multiple degrees of freedom? So what's going to happen when we don't have 2 by 2 matrices, where we don't have just one Q and P, but you have, say, Q1, Q2, and P1 and P2, right? So this would be the space that I'd like to study, and quite frankly, I don't know how to do it. Some things remain similar in the sense that even in this case you're going to have a symplectic form, which is going to take this form, but now these ones are actually, let's say, i's. These are 2 by 2 identity matrix, so it's something like this, right? So if I have to spell this out completely, it would be 0 0 0 0 1 1 0 0 1 1 0 0 with a minus, and then 0 0 0 0. So this is the full symplectic form. And then the symplectic group, the groups of linear transformation that are also essentially canonical transformation, therefore come from Hamiltonian motion, would be essentially written like this. You would look for things where, again, this equation is satisfied. And if you write J as a block matrix, right, you are going to find that you will need some conditions, because when you go and do the products, you are essentially creating a product of these block matrices, and you're going to find that some of them, those products, are 0 and some of them are going to be 1. So let me go get the correct relationship, just that we can write them. A transpose C minus C transpose A is equal to 0, and then B transpose D minus B transpose D transpose B. D transpose B is equal to 0, and A transpose D minus C transpose B is equal to the identity. I don't know you, but these equations don't tell me absolutely anything of what's going on. But in principle, these are the constraints that you get. So the elements of the symplectic group are those and only those that satisfy these equations. And what I really need to understand is what this means. What do these constraints mean, if anything, to how the covariance matrix evolve. And my hunch is that this decomposition is not going to be the one that we want, because what happens is that we are decomposing essentially. These are all the Q's, these are all the P's, and these are all the Q's, and these are all the P's. And so these essentially tells us how the Q mix, and this is going to tell us how the Q and P mix, and the same with this one, and this is telling how the P's and Q mix. And really what I think is the correct a physical thing to understand is how the uncertainty that we have in different degrees of freedom is mixing with each other. I think that's really what we would like to understand. And for doing that, if we look at the expression of my covariance matrix, I don't want to have something that is like sigma q1 square, sigma q2 square, sigma p1 square, and sigma p2 square, and these are all the different possible covariances. I don't want to look at that. What I'd like to look at is something like q1 square and p1 square, and these are going to be the covariance within the degree of freedom. And I want to understand this as sort of the block matrix. Like, I want to understand what happens to that, because I know that if that were a single degree of freedom, the determinant of that would remain conserved. And so I'm kind of trying to understand what happens to that determinant in multiple degrees of freedom. And the other degree of freedom is going to be sigma q2 square, sigma p, no, this is q1, no, q2, sorry, q2 square and p2 square, and these are the covariances, right? And then essentially here we would have this sort of covariance, we have the correlation across the degrees of freedom. And so my hunch is that what kind of probably is going to happen is that you have uncertainty here, and then you move it in a sort of correlation, and then you can move this correlation in here and sort of do. That's kind of what I want to understand, if at all this makes any sense mathematically, if it works. Essentially, how do these correlation sort of travel from one degree of freedom to each other? And because again, there is going to be a subgroup of these transformation where you are just acting on the 2 degrees of freedom independently, and therefore you're going to be preserving the uncertainty on each degree of freedom and not putting any correlation. And again, the idea is I want to understand what you can do apart from that. Can you introduce a correlation? But then when you introduce correlation, are you increasing the uncertainty on both degrees of freedom? Can you trade off one uncertainty for one degree of freedom with respect to the other? I don't think you can do. I don't think, for example, that you can increase this and decrease the uncertainty in this and not put any correlations at all. And in fact, I mean, still the determinant of this whole thing is going to be is going to be half preserved. So if we imagine that we are in a situation where we don't have any covariance, any correlation across degree of freedom, so that the total determinant is the product of these two, right? The only way that we can increase the product of these uncertainty is to introduce some correlation, because otherwise, the determinant of these would be coming in with the minor. So maybe you can introduce. No, because this has to be symmetric. I mean, so there are some constraints on this matrix, because the matrix that we're looking at mathematically can be understood as a symmetric and positive definite matrix. So essentially, mathematically, we're trying to understand how a symmetric and positive definite matrix evolve through the symplectic group. I mean, it's a well-defined problem, but we want to understand it in this block diagonal form. So this is what I kind of feel that it should be not such a difficult problem. It should be probably something that that even if you have knowledge of undergrad level physics and math, it shouldn't be impossible, because it's all linear algebra. It's all understanding how, what can happen, and at the end of the day, once we study the 2 degree of freedom, right? Once we study these 4x4 matrices, we have understood the whole thing. So in principle, one could just do even just simulations of this and see what happens and get some intuition, and then we find it in the math. So this is, I think, an open problem that I have. And again, I think it might be fun. It's just I don't have the time to go and look at it. I sometimes play around with this, and then I don't find a simple solution, and then I start doing other things. And so I think that maybe this is something that, I don't know, some of you can work out or find the solution, because I still am surprised that nobody would have mapped this out. But then again, a lot of other things that I do are surprising that nobody has looked at. So anyway, I think this is a simple problem, so I thought I would make a short video, and if anybody has insights or knows how to solve it, they can leave a comment in the comment section, or if you are shy, you can always write an email. But I'd rather really that we have discussions on the channel, so that it also drives the video. Okay, thank you again, and see you next time.